Hey, hello. This is Junichi Horikawa. I'm gonna start the live streaming for today. This is the weekly live streaming Houdini tutorial. This week's theme is to create a simple setup for the Tensegrity physics simulations. All right, and today I'm going to. The live stream starts at 8 p.m. Normally it starts at 9 p.m. in Japan time, but I kind of have a thing to do tomorrow, so I'm going to faster in the time. Sorry for that. Alright, so let's get going. If you're curious how the setup is done, you can also download the zip file from the video description from this YouTube video. So if you're interested, you can download the zip file for the Houdini in the 18th, and there's a link to this GitHub page where you can download the file for this tutorial. Right, and let me just show you how it's going to be look like for the final output for today. So here I have some setup for the Tensegrity. The blue one is the rigid poles, and white lines are the wires which have some rubber-like stiffness, a low stiffness compared to the rigid blue ones. And if I play it, I can kind of simulate this Tensegrity simulations where the whole structures will stand up based on the composition of those wires and rigid poles. So that's what I'm going to do today, and the setup itself is pretty easy. So today's motivation for me is to just show you how you can actually set up this kind of Tensegrity. And one that I have chosen as a final output is this icosahedron Tensegrity, which I thought seems like a really simple sample that I could simulate. So this is the one that I'm going to create, or maybe this could also be the one. Right? So let me just show you how to do that. And for the physics engine, I am going to use a Vellum in Houdini, which is new physics engine simulations implemented in Houdini, and that's kind of easy to use one. So that's the things that I'm going to use. The only thing is that Vellum doesn't really have the rigid body constraints, so I'm going to kind of hack the parameter in order to create rigid-like geometry, rigid-like constraints using Vellum. So that's the only part what could be interested in this simulations. Other than that, it's pretty simple setup. Right. So first of all, I'm going to set the background to black so that I can see it clearly. And first of all, since the base geometry is the output is based on the icosahedron, I am going to create starting by the icosahedron geometry, and that you can create it from this platonic node. And from solid type, you can choose icosahedron, right? Just like this, and go back to the image that you want to create. Maybe I can zoom into this geometry a bit to see the character of this one. And I can see that first of all, the wire is kind of similar to the wireframe of this icosahedron, so I am going to keep this wireframe as the wire. Seems like some of the wires has been trimmed like these ones, so not all the triangles has been preserved, but just to make it simple, I'm going to preserve all the triangles. For the wires, maybe I can reduce it later on. And for the rigid poles, in this case, this wooden pole is being created. The total number of wooden poles are 6, I think. 1, 2, 3, 4, 5, 6. And as you can see, not single poles are attached together, so all the poles are separated together but connected with the wires like this. So if I look at this triangles at top, you see that there's 3 different poles being attached at the vertex and then attached to the bottom part of this icosahedron, and other 3 parts is connected underneath in another triangles. So keep that in mind, and let's start by creating a rigid pole lines from this icosahedron. So to make it to be able to see the inside, I am going to set the shading to wireframe first, like this. And let's think about where to create a rigid poles. And I'm gonna look at this top triangle as a base to create a triangle, I mean the rigid pole. And let's look at the number of primitive and number of points, and also let's set the text guide to be a bit bigger, like this. Right, so the first pole position, let's think about first pole position, and one could be from, say, let's say this is number 8, right? And this is number 2, and maybe start from the top part. So there you have point number 10 around here. And from this point number 10, I want to create a pole, rigid pole to some of the point, and that point could be either from the photos that I am looking at. This the point that should go, it could be from 10 to 7 or 10 to 0, I think, somewhere around here, or to 10 to 7 or 5, maybe 7. So I'm going to create a pole from 10 to 0 for now as an initial rigid pole, and I am going to copy that pole by rotating it 120 degrees using this plane as a guide, so that it will create kind of a mirrored shape, mirrored rigid poles based on this triangle, which is numbered as 10 right here. Right, so let's do that. And first of all, in order to use this plane as a guide, I also need the normal direction of this plane in order to create a rotation. So first I'm going to create a normal primitive normal using the normal node. Then I am going to use the attribute wrangle to create a rigid poles. Let's name this rigid, and let's start by writing the code to create this rigid pole kind of procedurally, but it's a bit hard-coded since you have to choose the number that you're going to use. So the first point number that you want to pick up is 10 and 0, so let's get that position by point, and maybe I would like to use this as a detail wrangle and then connect this primitive as a guide. So I'm going to connect it to the second input so that as a result I could have only rigid poles, and I could ignore the primitive details, primitive geometries that should from the output. So as an output, I should only have the rigid pole lines. All right. So from the second input, I'm going to get the point position from number 10. Also get the point from number 0. And also let's get the normal direction of this triangle, which is at primitive number 10. So prim second input normal at 10. All right. Now from this, I'm going to first create first primitive, which is the line connecting number from number 10 to number 0. So let's use add prim function to create a polyline connecting PT1 and PT2. Right, let's look at this, and okay, I have an error. Okay, that is because I have to add the point first. So first I need to add the point to this position 1 and PT2 as position 2. Then I can do like this. Right. So I have created initial rigid line, and let's also check the initial geometry, initial icosahedron geometry, and now I see that the initial rigid line has been created like this. Now what I want to do next is to create similar lines connecting from other vertices of this top triangle. So one from here and one from here. To do that, I can just rotate this lines using the center of this triangle and rotate it using the normal of this triangle. All right, so to do that, I'm going to create a matrix, to create a rotation matrix, and then I also need a for loop in order to create 3 lines for this triangle. So I'm going to cover this whole code with this for loop like this, right? And then do the rotation based on the number I here, integer I. So, and for each iterations I need to rotate 120 degrees, so I multiply by radians 120 degrees. And using the norm, which is the normal of the triangle, as a rotation axis. And the rotation center is, since this icosahedron is created on the center of the whole space, I don't really need to set up the rotation center because it is 0, 0, 0. So that this should be fine as a rotation matrix. And then after doing this, I want to rotate position 1 with a matrix, rotation matrix, position 2 as well with this rotation matrix, and as a result you can get those 3 lines rotated from the initial position. Now I want to do the same thing for the bottom part. So for bottom part, maybe I could use this plane as a guide to rotate, to create another 3 lines connecting maybe from, if I look at the number of the vertices, maybe from 8 to 2, and 3 to 5, and 4 to 11. So let's do kind of a similar things that I did like this, but with different numbers. So before I was using 10 and 0, but for now I would like to use 8 and 2 to create another lines from the bottom, and use this number 7 primitive, number 7 triangle as a guide to rotate the lines that I'm going to create for the bottom. So to keep it simple, I'm going to create another loop with 2 iterations like this. And I'm going to change those numbers based on the number of n. So if the n is equal to 0, then I would like to use these values, 10, 0, and 10. But if the n is equal to 1, then I'm going to use 8, 2, and 7 for the primitive number. Right, so to do that, I think I need to have the variable position 1, position 2, and norm outside the if condition. So let's have this outside somewhere around here like this, and then if n is equal to 0, use these functions to update position 1, position 2, and norm like this. Else, there's only 2 iterations for n, so else means if n is equal to 1, then I'm going to just copy this and change those values from 10 to 8. So 8, 2, and 7. Okay, let's see how it goes. If I apply it, and if I toggle on the visualization of this attribute wrangle, it seems like I have done it correctly to create 6 poles, 6 lines in order to make it use it as a rigid pole, something like this, right? Okay, I think it looks good. Let's compare with the image, and cannot really tell if this is really correct, but I think this is correct. No single rigid poles are touching to each other, but those are just connected with those wires. So I think these are correct, hopefully. All right, so let's get going with this. Okay, now after doing this, I'm going to apply a group to this poles that I have just created. I want to create a group, maybe naming as a rigid. Could be any name, but I'm just doing it in order to split it later on in order to visualize the wires and rigid lines differently. All right, and what I need now is a wires as well. So for wires, I'm just going to use convert line and convert this icosahedron shape to a line connection like this, just that. And I'm going to name this, I'm going to put this in a group called wire for these one. right? That looks good. And now I'm going to merge these together, maybe to make it able to be able to see the difference between the rigid and the wires. Maybe I'm going to set the color for the rigid, maybe something to red for now. I might going to change it later on. And for the wires, I'm going to set the color to blue for now. Okay, like this, so that I can see the difference between the rigid and wire lines. Okay, now currently I have just merged it, but there are duplicate points where rigid poles and wires are connected like this. So in order to create the simulations, physics simulations, I need to merge these together, fuse these together. So, oops, what I have done. I'm going to use fuse to weld the points together, and now the color is gone. All right, that. Well, forget about the colors, or maybe I can set the color as a primitive. All right. Okay, and let me also save this just to make sure I won't lose anything. Okay. Now the whole setup, the geometry setup is done for the simulations. What I'm going to do now is to create the constraints, actual physics constraint for the Vellum in order to create the Tensegrity structure simulations. Right, so let's do that. And I am going to use a really simple Vellum constraints. Vellum constraints, this one. This is the most simple constraints for the Vellum, and connect this with this wire lines, wire and rigid lines. And for initial value, I cannot really choose whether rigid or wire. Even if I choose rigid or even if I choose wire, the whole stiffness or other parameters is going to be added to every primitive which exists on this setup. So this doesn't really do much. So I'm going to just clear the filter, and the first thing I'm going to do is to set the stiffness for either wire or either rigid. And I'm going to later on change the stiffness for other geometry. If I choose the stiffness for the rigid right now, then I'm going to change the stiffness for the wire geometry later on using some wrangle. Right, so first I'm going to set the stiffness for the rigid, and the stiffness means the hardness of the constraints, and right now the constraint type is set as distance along edges. So this is like a constraint works like a spring, and more stiffness you have, the harder the strings will become. And there are no like such thing as rigid springs in Vellum. So in order to make it rigid as possible, you need to make this stiffness value really high. So for the rigid poles, I'm going to set the stiffness to 10 multiplied by 1e plus 10. So it will be really high stiffness. It will have really high stiffness. If you think it's not enough, you can increase this by adding more zeros to this. But I think 10 will be fine for now. Right. So if you look, by doing this, you can create the constraints for whole lines exist in this geometry setup. And you can check that by connecting a null node to the middle output, which is actually the constraint geometry. And if you select this one and check the geometry spreadsheet, and go to the primitive wrangle, primitive attribute, you can see whole sets of attributes which relates to the constraints of these lines. And the only important things for now that you have to check at is this stiffness value right here. So as you can see, you have currently total of 36 constraints, which is equal to the number of lines of this geometry. So every single line has been converted into a spring constraints, and every single line have this same stiffness, which is equal to 1e plus 11, which is really high stiffness. So currently all the lines is acting as a rigid pole, but that's not the case that's not the case for me to actually simulate the Tensegrity. In order to create the Tensegrity simulation, I need to set those blue lines as a wire, so must have much lower stiffness in order to make it like a rubber-like wire. So we need to change this stiffness only for this wire geometry, but as you can see, the group is also taken away. All the group rigid and wire become 0 when I have created this constraints. So I kind of need to find out which one is wire and which one is rigid. So that's where you need another wrangle in order to find out which one is wire to set up a new stiffness. Right, so I'm going to use a primitive wrangle to find out which one is wire and set up the new stiffness for this wire. Right, and that should be really easy to find out because you already have the guide geometry, which is this one. Before creating the constraints, you already have this set of geometry created as a wireframe, wire lines. So I can use these as a guide to find out which one is which one is wire and which one is rigid. So I'm going to connect the middle output, which is the constraint geometry, to the primitive wrangle and connect this wire geometry to the second input as a guide. And I'm gonna name this wire stiffness. Right. And then let's write some simple code to find out which one is the wire geometry. Right. To do that, I can just check the distance from each primitive constraint geometry's center point. So each line has the center point, which you can access by @p in primitive wrangle, and I can use this @p to get the shortest distance to this guide geometry. So if the shortest distance is equal to or less than really small number like 0.001 or equal to 0, then that means that the constraint geometry that I'm looking at right now is actually the wire geometry. If the distance is more than 0.01 or really far from 0, then that means it is not really close to this wire geometry, which means that is equal to rigid poles. So I can just get the distance, shortest distance, by using a function called xyz_dist, checking the second input with the center point of each primitive constraint geometry is primitive. And then if the distance is really small, like less than 0.01, then that means the geometry that you are looking at right now is wire. So for that, I'm going to change the primitive attribute called stiffness to a new value, and I'm going to parameterize this so that I can change it later on, like this. Okay, apply, accept, and promote the attribute. Let's have this parameter with the inside the null node named controller so that I can access it to this parameter by accessing to this null node. And let's set the range of this stiffness wire. I'm going to name this wire stiffness as a float number. And I'm going to set the range from 1 to, say, 200. Right. And let's copy this parameter. Go back to the wire stiffness wrangle, and I'm going to copy paste relative reference. And then the parameter will be linked. Okay. Now let's again check the primitive attribute for this constraint geometry if the stiffness has been successfully updated. So as you can see, there are two types of stiffness, one with this IE plus 11, and I have only 6 primitive which have this number, so that means these are the rigid poles. And other primitive have 84.2, which I have set it by myself using the slider. So these are the stiffness for the wires. So as you can see that I have set the stiffness for the wire really low, much lower than the rigid poles. That means I am making the physicality, the stiffness of the wire really low to make it really like a rubber-like spring, so that it can extend or shorten pretty easily compared to those rigid poles, which is pretty hard to move the lines. I mean scale the lines. Right, so the constraint is already ready. So what I just need to do is to connect this to a Vellum solver, and that's pretty much it. Connect this to the first input. For the constraints, connect this to the second input. So this is the modified constraints, and for the third, which is equal to collision, just connect to the third input from this constraints. And for the solver, I'm going to set some ground so that it will hit the ground when it touches the ground when it falls. It also have the gravity force, and so I'll keep it as it is. And right now, as you can see, the geometry is up in the middle of this ground, so let's set the ground position as it's a bit lower to minus 0.5 or something. Maybe minus 1. Alright. Okay, let's test this out if the initial simulation is working, and if it works, then I'm going to modify a bit to make it a bit more interesting, and I will finish this live for today. Okay, if I play it, okay, it falls, looks like it's working. I cannot really see if the red is really working as a rigid or if the blue is working as a wire, so I am going to set the stiffness of the wire a bit lower, like 25, to see if the blue one is really acting as a rubber-like band wire. Okay, let's see again. Okay, now it seems like it does, and the red one is really not changing the length, but only the blue one is bouncing, creating this kind of simulations. Okay, I think it is going okay. Now, next thing I would like to do to try Next thing I would like to try out is that this thing still works even if I change the scale of this whole geometry. Something like squashing this geometry, scale this geometry in y direction, make it really small, like using a transform, and set the scale for the y direction to 0.1 and creating a squashed geometry like this. And this still works because all the constraints geometry, all the constraints property is left in this attribute, such as the rest length, which corresponds to the final length that each lines want to go to, and all the stiffness is as it is. It doesn't really change what that is. So that means even if you change the whole geometry after you created the constraints, you can still keep those properties of this physics. So as a result, you should still be able to get the final result like this. Now that's the interesting part of this Vellum. Now there is a bit of problem with this if you are seeking for more realistic simulations, because when you scale down this geometry to y direction, maybe it's okay to change the size of the wire because the wire is pretty possible. It might be possible to change the length of the wire by pulling or pushing with the lower stiffness, but in physical world maybe it's not possible to change the length of those red one, which corresponds to the rigid poles. If it's made of wood, maybe it's not possible, or it's not really possible to change the actual length. So starting with this kind of squash geometry might not be realistic. So to make it a bit more realistic, I can have additional setup to set the length of these red one same as the initial length, which is equal to the one that's before scaling this down. So currently, and I can check the length of the geometry by using the measure node, maybe somewhere around here, and use the parameter as a measure type. And if you go to the primitive, you can check the length of each primitives, and the one that has group called rigid have this parameter, original parameter like this. When you scale down the whole set geometry with the scale, a transform, and if you check the parameter again, then as you can see, the parameter of each lines has been changed by using this scales, and well, it's going to be replaced with the original parameter because you already have created the constraints based on this previous parameter. So that's not really a problem after you have started the simulations. But if you want to make the starting point to be same as this line length, then you kind of need to modify this geometry, maybe in my case using primitive wrangle to set the length for each rigid lines. Now that is really up to you if you want to make the initial setup bit realistic or not, but I would like to do it for myself, so let me just show you how to do that as well. So I'm going to only change the length of rigid, so I'm going to filter out with this rigid group, Then to change the length, I'm going to first get the point list for each primitive. In this case, each primitive has 2 points, so I can get it by accessing to the points using prim points function, vex function. Then for each point, I'm going to make a loop like this, right? And then get the position using the point number that I have just get. Okay, and next thing I would like to do is to create the direction. So currently I have, let's say that I want to change the length of this red primitive line, right? And then if you're in the primitive wrangle, by accessing to add p, you can always get the center point of this primitive. And in this loop, I'm getting the end point of this primitive, which is at this point and at this point. So by having the center point and the end point, you can first get the direction from center to each end point, which means you can get the direction where you want to grow this line to grow to. And after getting the direction, you want to have the guide lengths you want to use in order to modify the actual length of this rigid length. So you can get the guide lengths probably from this measure node that I have just attached. So I am going to attach this measure node to the second input of this length primitive wrangle. And let's first calculate the direction from center to each end by position minus at p. At p is the center point of this primitive, and normalize this so that the length will be 1. The vector length will be 1. And now let's create the new position where you want to move those 2 endpoints so that the final rigid pole length will be equal to the one that I have calculated right here when I have used the measure node. Right, so to do that, I might need to get the guide length first from this measure node, and the name of the attribute was parameter. So let's access to this parameter attribute first. Inside is primitive wrangle somewhere around here. I'm gonna name this rest length and access it by using prim second input parameter and add prim num like this. Okay, and the new position that I want to create is from the center point plus direction multiplied by rest length that I have just calculated, retrieved from the measure node. Then make it half because you want to pull to the left and right at the same with the half length from the center. Okay, and then finally set the point attribute for each endpoint like this using the newly created position. And now maybe you can see the changes before and after. I have just modified the point position of each rigid point endpoint to make the length same as before, same as this measure node. Before it looked like this one, but after applying this primitive wrangle, the whole geometry have been scaled up. And let's check the actual length using another measure node if it has been really corrected, if the rest lengths have or has been correctly modified. Setting the measure type to perimeter, go to the primitive and check the rigid group, and as you can see, all the perimeter has been corrected, same as the rigid pole lengths calculated at this measure node, same as this one. The wire length is still different, but that's not really a problem because it is, you can assume that these are like stretchable. Alright, so now let's simulate this again, and it still works just fine. Now I'm going to end this by actually visualizing those lines to geometry, like using polywires, and I will end this live. Okay, so to visualize this, I'm going to first split the final output to rigid and wire primitive. Going to say rigid for this one. So from the left output, the rigid wire is going to be outputted. Okay, do I see anything? Where is it? Okay, I think I need to set the shading to shade it. Okay, I still don't. Okay, maybe I need a normal, renormalize this later on. Yeah, okay. Now let's also create the polywire for the wires as well. And I also need to normalize this. Okay, now there are too much thickness for these, so let's set the radius for the wire type to be 0.005, and then for the rigid poles, I'm going to set the wire radius to 0.05, and let's also set the divisions to 6 or something to make it a bit more round, maybe 8. And for the wires, I really don't need to increase the divisions because it's a bit hard to see if it's round or not, so maybe keeping it 3 is fine. Okay, now let's color this so that I can clearly see which one is which. I'm going to set the rigid pole to be orange for now, the wires to be white, maybe, and then merge these together, and that is it. This is the final setup for this Tensegrity structure system. Okay, now after I have played this, you can kind of assimilate this kind of Tensegrity system. Alright, this works fine, and if for today there's only one parameter that I can change, it is this wire stiffness. So let's try this by changing the stiffness to 10 to see what would happen if you make this wire a bit more softer, a bit more stretchy. Okay. Now you can see less rigidness to this structures. Interesting. Make it 30. Bit more harder. Still bouncy. If I make it 100, it becomes more rigid. Okay, that's pretty much it. Other thing you could try is reducing the number of wireframe lines. I am not going to show it programmatically, but let me just try it manually by reducing the wire. At this point, maybe I can delete some of the lines, which might not be necessary. So let me select some of the primitive like these. Randomly, I'm just going to randomly pick up some of the points like these, maybe like these, and let's say what could be the other, like this. Okay, I'm going to maybe not this one, since this is connected with this line. Right, maybe this one. Okay, so let me try to delete those wires and see what would happen if I don't have those lines as a wire, and see if this still works. Okay, if I play it, seems like it still works, even if it's missing some of the wires. Maybe it became more bouncy than before. If I set the rigid to 100, does it make changes? Okay, I think it became a bit more bouncy even when the stiffness is equal to 100. But as you can see, you can try out like various setup for this Tensegrity just by removing or adding those lines, and you can try out many stuffs, many simulations, which could be feedback to the physical world later on in order to create the actual thing. Who knows? So that's it for today's live. I hope you find it interesting, and let me know if you have any questions. If not, I am going to end this live. Yeah, and I have finished this live in 1 hour. Good for me. All right. Thank you all for the comments as well. Okay, I guess there's no questions, so I will end this live at here. Thank you very much, and I'm going to leave this video as an archive so you can watch this later on if you're interested. And you can also download the file from the link attached in the video description. Thank you very much, and goodbye.